Have you ever tossed a pebble into a pond and watched the ripples spread out in perfect circles? That simple, mesmerizing effect is a great starting point to understand one of the most fundamental concepts in physics, wave mechanics. Waves are everywhere, from sound traveling through air to light reaching our eyes, even the seismic tremors during an earthquake. But what exactly is a wave? And how does energy move without the medium itself traveling? In this explainer, we'll break down the basics of wave mechanics, how we perceive waves before diving into how they're generated, and why this understanding is crucial for phenomena like the Doppler effect. Let's start with that pebble dropped in a pond. The moment it hits the water, energy is transferred, creating ripples that move outward. These are called radial waves. They propagate equally in all directions from the source. Notice something important here. The water itself isn't moving outward. Instead, the water molecules oscillate up and down, transferring energy to their neighbors. Imagine this guitar string made up of countless tiny particles. When plucked just off-screen to the left, energy is injected into the string. But what happens next isn't a simple flow of matter. Instead, watch closely. The wave carries energy from left to right, yet each particle only moves locally, up and down, before returning to its original position. No single dot is swept along. The material isn't displaced. Only the energy travels. This graph tells the story. Dot A oscillates first, then dot B, with the same pattern, just delayed. Their motion is identical in shape, but out of sync. Notice how neither dot drifts upward or downward over time. They vibrate temporarily, then settle back. The energy moves through them, not with them. And so the wave delivers its energy forward, without carrying the material itself. A disturbance in place, a transmission in motion. Now, here's a crucial point. Not all waves travel the same way in every medium. The medium's properties determine how well energy propagates or doesn't. Take water, for example. Sound waves travel exceptionally well through water. That's why whales can communicate across vast ocean distances. But radio waves? They barely penetrate water at all, which is why submarines use sonar, not radio underwater. On the other hand, consider air. Sound moves efficiently, but light, an electromagnetic wave, doesn't need a medium at all. It travels through the vacuum of space. Meanwhile, seismic waves move through the Earth's crust, but they're quickly dampened in loose soil. So when analyzing waves, always ask, what's the medium? Is it obstructive or transmissive for this type of energy? So, what's the takeaway? To truly understand a wave phenomenon, whether it's sound, light, or ocean waves, we must start by carefully observing how the wave behaves in its environment. By noting frequency shifts, amplitude changes, and how the medium affects propagation, we can work backward to uncover the source's behavior. This approach is fundamental in fields like astronomy, detecting distant stars, medicine, ultrasound imaging, and even engineering, noise cancellation. In future episodes, we'll explore more about wave generation, interference, and the Doppler effect in depth. But for now, remember, waves transfer energy, not matter, and the medium dictates how that energy moves. Next time you see ripples in water or hear a distant sound, think about the invisible energy traveling towards you and the fascinating mechanics behind it. Thanks for watching, and stay curious.